Hello, my name is Dimitris Kitharidis and I am leading the research group of Intracom Telecom's wireless division. In MARSAL, we have shown that the introduction of the inter-ODU coordination is critical for enabling the full potential of the cell-free massive MIMO network's deployment, improving the spectral efficiency but at the cost of increased user and control plane load. This coordination can be supported through the inter-ODU coordination interface, which is currently not defined in the open standards. In this video, my colleague George Kapsalis will show you the results of our joint work with IS Wireless in the development and validation of our proposal for the inter-ODU coordination interface through a wireless high-speed low-latency link at the E-band, actually at 7484 GHz for the two directions, that will meet the increased performance requirements for the ODU to ODU communication.
Hello, my name is George Kapsalis and I work in the research group of Intracom Telecom's wireless division. In this video, we will show you our joint work with IS Wireless and MARSAL in the development and validation of an inter-ODU communication. For the execution of the demonstration, a server hosting the two ODUs was employed, equipped with high-speed network interface cards along with two radios that implement a millimeter wave link.
The two 10 Gbps NICs are connected to each other through ICOM's millimeter wave link, while the corresponding virtualized DUs from IS Wireless have been implemented in such a way that they send and receive traffic to and from the NICs. DU1 is bound to NIC 1 and DU2 to NIC 2. The equipment used in the millimeter wave link deployed to set up the communication infrastructure that will transfer data between ODUs is called Ultralink GX80 and belongs to the Ultralink family of outdoor radios manufactured by ICOM, offered as a solution for demanding gigabit data transfer application. The most important KPIs selected to evaluate the testbed were throughput and latency in order to investigate whether the user plane data communication through the proposed inter-ODU link could be properly served. In order to demonstrate the validity of the concept of the inter-ODU communication, a modular approach with three phases was employed, each one targeted to measure the throughput capability and the latency attributed to the millimeter wave link and the ODUs respectively. In the first phase, the experiment consisted of a setup with the ODUs deactivated and NICs connected with a fiber cable loop in order to measure the latency for the computer server to transmit packets from NIC 1 to NIC 2, effectively defining the baseline for the experiment. To measure throughput, Hyper-3 was employed, a tool for active measurement of the maximum achievable bandwidth on IP networks operating client-server mode. The Hyper-3 client was bound directly to NIC 1 and acted as a packet generator, while the Hyper-3 server listened directly to NIC 2. As Hyper-3 is not designed for latency measurement, the ping command was used to add ICMP echo request packet to the UDP stream generated from the Hyper-3 client and subsequently measure the latency of those packets. In the second phase, the DUs were activated and by comparing the results with the measurements obtained in the first phase, an estimation of the latency inserted by DU was calculated. To measure the latency, the DU1 was adding the timestamp to each UDP/IP packet based on the server clock and was sending the UDP/IP packet to the DU2 through either fiber loop or millimeter wave link. After reception of the UDP/IP packet with timestamp, the DU2 was checking the current system time and calculating the time difference between the current system time and the received timestamp. At the third phase, the fiber loop was replaced by ICOM millimeter wave link in order to measure the latency attributed to the wireless link by comparing the results with those of phase 2. Eventually, the total latency of the proposed inter-ODU link was measured. In order to demonstrate the validity of the concept of the inter-ODU communication, a modular approach with the three phases explained earlier was employed, each one targeted to measure the throughput capability and the latency attributed to the millimeter wave link and the ODUs respectively. By selecting a fixed bandwidth value, phase 1 aims to measure the server latency, while phase 2 measures the latency attributed to the ODUs, and finally phase 3 measures the latency of the millimeter wave link. This demonstration aims to show the modular approach of the three phases for fixed bandwidth at 8 Gbps. Grafana real-time visualization are employed in order to create a real-time presentation of the measurements. In the first phase, the experiment starts with server and fiber loopback as a baseline experiment. The computer server fiber loopback architecture presents a latency of approximately 100 microseconds. Then in phase 2, the ODUs get activated. The latency rises at 250 microseconds. Comparing the results with phase 1, the ODUs have added approximately 150 microseconds to the baseline hardware infrastructure. Finally, in phase 3, the fiber loopback is replaced by ICOM's millimeter wave link. The latency of the proposed hardware infrastructure at 10 Gbps is approximately 325 microseconds, and by comparing the result with phase 2, around 75 microseconds is attributed to the millimeter wave link. This experiment is repeated for different bandwidth values, in order to showcase how bandwidth affects the latency of the inter-ODU communication infrastructure and each component. In this demonstration, the purpose is to investigate throughput latency variation. During the demonstration, the hardware infrastructure is that of phase 3 with the DUs activated and the millimeter wave link on. Bandwidth varies from 4 Gbps to 10 Gbps with a step of 2 Gbps. Starting from 4 Gbps, latency is measured at approximately 200 microseconds and throughput at 4 Gbps. At 6 Gbps bandwidth, latency slightly increases at approximately 225 microseconds while throughput increases to 6 Gbps. Then, increasing bandwidth to 8 Gbps, latency rises to approximately 275 microseconds while bandwidth is still fully utilized, resulting in 8 Gbps throughput. Finally, when hitting the max limit of 10 Gbps bandwidth, latency abruptly rises to approximately 400 microseconds while throughput presents a saturation point at approximately 9.4 Gbps. Here we can see the variation of the latency inserted by each segment of the signal chain with respect to bandwidth, and the CPU usage variation when bandwidth was increased. Latency from computer server shows a dependency on the bandwidth used to transmit data. Latency inserted by the DUs was strongly dependent on bandwidth attributed to the more intense packet processing taking place in the DUs and varied between 95 and 205 microseconds. Latency inserted by the millimeter wave link was independent of bandwidth and was measured in the range of 75 and 90 microseconds. Throughput and bandwidth were proportional, but when approaching full capacity at 10 Gbps, throughput presented a saturation point at 9.4 Gbps.
To conclude, our experiment successfully demonstrated the validity of our proposal for the implementation of the inter-ODU coordination interface through a high-throughput, low-latency millimeter wave link that meets the requirements of such an interface in a cell-free Open RAN network architecture.